For part C, let's do the same. Let's apply the same approach. A n is n factorial squared, and then 3n as a number factorial. Okay, it's not 3 times n factorial, but 3n is a number, whatever n is, right? And then starting from 3n, you go all the way to 1. So it's the product of all numbers starting from 1 all the way to 3n. Okay, so absolute value a n plus 1 over a n. Okay, that is equal to n plus 1 factorial squared. Well, I'm going to replace n by n plus 1 in the bottom, so it's going to be 3 times n plus 1 as a number factorial. So it's 3n plus 3 factorial. Okay, and this is divided by an, so I'm going to flip over an because that's going to be in the bottom. So to save space, I'm just flipping that over right here. Okay. All right, so now I got to simplify this, and I'm going to use the properties of factorial. So first of all, n plus 1 factorial is n plus 1 as a number times n factorial. Okay, that's one observation. 3n plus 3 factorial is 3n plus 3, 3n plus 2 times, I'm just continuing from here, 3n plus 1. This goes all the way to 1, but starting from 3n going all the way to 1, that is 3n as a number factorial. So you can actually write one factorial in terms of the other factorial in both cases. So I'm going to use these two properties here. Okay. So I have n plus 1 times n factorial, and if you take the square of that, okay, the square of that is just this. I'm using parentheses here just to be very careful, okay? Otherwise, it's going to mess up, right? So 3n plus 3, 3n plus 2, 3n plus 1 times 3n as a number factorial, okay, times 3n as a number factorial and n factorial quantity squared. Okay, what cancels out now? Let's check. I have n factorial squared. I have another n factorial squared. They cancel out. 3n factorial, 3n as a number factorial. We divide them out. And what we're left with is n plus 1 squared at the top and the product of these three terms here. Okay. So let me continue with a new slide. All right, so now I'm gonna pass the limit. How do you pass the limit? Well, the top is a quadratic, the bottom is a cubic. So this limit should go to 0. Okay, and you can just see this by expanding this whole thing out. So you can expand the bottom out by just first expanding these two and then expanding the whole thing. Let me just do the long way so that you can actually see how I do it. 9n squared plus 6n plus 9n, so it's 15n plus 6 times 3n plus 1. I can expand this out, but I can also use the product rule. But anyway, because when you apply the L'Hopital's rule, you're going to apply the product rule for the bottom. But to avoid that, let's expand the whole thing. So 27n cubed plus 9n squared plus 45n squared, 54n squared plus 33n plus 6. At this moment, in fact, I can just pause the video and then go slowly and crunch those numbers. If I make a mistake here, disregard that, because all matters in terms of finding this limit is the leading terms. Okay, so all that matters is the leading terms here. But anyway, if you apply the L'Hopital's rule, because you have infinity over infinity type indeterminate form, At the top, you have 2n plus 2. In the bottom, you have 81n squared, 108n plus 33. Okay? And you still have infinity over infinity type indeterminate form. One more time, you apply L'Hopital's rule. You have 2 at the top. You have 162n plus 108. And there you go. So you still have an n term left in the bottom, whereas at the top you have no n term. So the top stays still, but the bottom approaches infinity as n goes to infinity. So it's 0. As like a quick tip for you, if the degree of the top is less than the degree of the bottom, the limit has to be 0. And this is sort of like a formal way of, or a longer way of proving it, but we could perfectly conclude that this would just go to 0, and which is good because 0 is less than 1, and going back to the description here, when the limit is less than 1, okay, then the series converges absolutely. So I can go ahead and conclude that this series converges absolutely. Okay.